Hello everyone, welcome to my video. This video serves as a companion to lecture 21S. We'll be looking at 3 examples in chapter 4, since this chapter is not explicitly being discussed in lectures, so I'm doing the examples here in the video. For each question, please make sure you pause the video and read the question before proceeding. In this example, we have 4 individual particles consist of a system where each particle's position, velocity, and external force are given. Okay, we have the position, the velocity, and the forces as it applied. So we want to find the first and second derivative of the position vector of the mass center and the kinetic energy of the system. Since our system is given with 4 individual particles, in order to find the position vector of the mass center, we need to find the position vector of each individual particle first. Here we have particle 1. We'll use R1 vector, the displacement vector of particle 1 is 2dI unit vector minus 2dj unit vector because it's on the 2d positive x direction and 2d negative y direction. Okay. Similarly, we'll find it for particle 2, which is right here. We'll find it for particle 3, right here, negative 2d on the x direction, and particle 4, right here, positive 1d on the y direction. Now, with the position vector of each particle, the mass center position vector, R bar, can be calculated using this weighted average formula. Sum of mi ri of each individual particle divided by the whole mass, all added together. In this case, all mass added together, we have m, 2m, 3m, and 4m. And on the top is m of individual particle. For example, this is particle 1, this is particle 2, this is particle 3, and particle 4. Adding them all together, divide the whole mass. This is the weighted average formula. You should recall this from your stats course. Then we can get the position vector R bar, which is pointing from the origin to the mass center of the system, wherever this is according to their positions. You can imagine this in your own mind. This will be 0.4, a little bit on the x negative direction, and 0.2 a bit here, and 0.3 is somewhere, probably somewhere here. Right? It kind of makes sense because the most mass is 2m, 3m, 4m is here, so your mass center will be close to the heavier side. Next, we'll look at the first derivative of R bar, or say R bar dot. Or you would realize that this is the velocity, right? Hopefully you can realize that. The derivative of displacement is velocity. Since the velocity of each particle is already given on the diagram, see the square root 2v, and v, and v, and v here, we will just copy them over, and we have the particle 1 as negative v, I direction, the x direction, y direction, z direction, and the x direction. And similarly, again, we'll be using the weighted average to find the derivative of mass center position vector R bar dot. Okay, it's very similar to what we did on the previous slide. In this case, you're just doing the replacing the displacement with the velocity in this case, and you can find the average velocity of, or the mass center's velocity in the vector form in this case. Here you have the v. Now finally, as for the second derivative of R bar, the mass center position vector, I hope you can also realize this is the acceleration. And we have the displacement, then we have the derivative of displacement is velocity, then take the derivative again, gives us acceleration. So after you realize this R bar dot dot, the second derivative of r bar is essentially the acceleration. Plus, looking at the diagram here, we see that forces are given. You have two external forces, one right here, one right here. So we have the force, we want the acceleration. What's missing? Mass, right? Now you can write the acceleration, or r bar dot dot, is sum of F divided by the sum of mass, right? Or the total mass of the system in the vector form. And we have the force in the vector form dividing the mass. So the r bar dot dot, the second derivative, is F over 10m. This is scalar I plus j. Okay, this is in the vector form. This is given by the sum of force equals to ma, because this is our acceleration here. Finally, the kinetic energy, T. By definition, we would need the mass and velocity, and it comes to 1/2 mv squared. With a system of particles like this, the total kinetic energy will be calculated by summing all particles' kinetic energy. So we have here the kinetic energy of the particle 1, of particle 2, particle 3, and particle 4. And of course, this 1/2 is factored out. Okay, this is particle 1, particle 2, particle 3, particle 4, and adding them all together give you this 11/2 mv squared. This is not a vector because energy is not a vector. Energy is a scalar. Next example, we have 32.2 pounds carriage A moves horizontally in its guide with a speed of 4 feet per second and carries two assemblies of balls and the light rods. When you see light rods, means the mass of the rod can be ignored, which rotate about the shaft at O, right here, in the carriage. Each of the four balls weigh 3.22 pounds. The assembly on the front face rotates counterclockwise at the speed of 80 revolutions per minute, right here. And the assembly at the back side rotates clockwise at the speed of 100 revolutions per minute, right here, 3 and 4. For the entire system, calculate the kinetic energy T. I'm going to pause here for a moment. How do we calculate kinetic energy for this whole system? If you're considering everything as a system, if I'm going to draw a system boundary here, essentially I can think there are 5 particles that consist of this system, which is particle 1, particle 2, particle 3, particle 4, and this big particle in the middle, like 5 particles. So to calculate the kinetic energy of the system, and since we have the system itself also on the move, as well as those particles inside the system on the move, we need to use the generic kinetic energy equation, which is defined as 1/2 mv squared, the v bar square, plus sum of 1/2 mi rho I derivative square, which the first part is the kinetic energy of the mass center. In this case, would be O, or the big block in the middle. And the second part is the kinetic energy of all particles relative to the mass center, which is 1 relative to the center, 2 relative to the center, 3 relative to the center, and 4 relative to the center. This is by definition, this is the generic kinetic energy equation. What you have a system particles on the move. Not only you need the kinetic energy of each particle, and you also need the kinetic energy of the particle relative to the mass center. So we'll start with finding out the individual velocity of each ball first. Since we have the velocity in the equation, in the question is given as revolution per minute. One revolution means 1 full circle, 2 pi, or 360 degrees. So we'll need to convert this revolution per minute into the standard imperial velocity unit, which is feet per second. Here we have this 80 revolution per minute. That means 80 full cycles, or 80 times 2 pi per 60 seconds. And this 82 pi is giving you the angular speed, omega. Right? The velocity, as you should also recall from chapter 2, the curvilinear motion, tangential velocity equals to radius times omega, or v equals to r omega, or v velocity equals to r theta dot. Okay, therefore we are also multiplying the radius here, but we're converting the radius from inches to feet. Okay, be very careful about the unit consistency here. Okay, the velocity is radius times angular velocity, or theta dot. This is what this is for. R theta dot give you the velocity. Then we'll be calculating the kinetic energy caused by the individual particles. Here we'll use ball 1 and 2 as an example, as they share the same velocity and distance to the mass center O. Right? They're all 12 inches apart, 18 inches apart from center O. Ball 1 and ball 2, or particle 1, particle 2. Here we have one more calculation built in here, because we need the mass for the kinetic energy calculation. The 3.22 pounds is not mass. Okay, it's pounds. Mass is in imperial unit is slug. So do not forget about that. Don't forget about your basic unit conversion skills. Also note that this two at the front, right? We have two balls. So you times 2 here. Particle 1 and particle 2. So for all particles all together, this is ball 1, particle 1 and 2. This is particle 3 and 4. And these 12.57 and 10.47 are the velocities of ball 1 and 2 and the velocity of ball 3 and 4. We calculated on the previous page. This is essentially 1/2 mass velocity square, the kinetic energy of particle 1 and 2, 1/2 mass velocity square, the kinetic energy of ball 3 and 4, times 2, times 2, all add together. These are the kinetic energies, the absolute kinetic energy of each particle. Okay, pay special attention to the energy unit under the imperial system, which is feet pound is your standard unit for energy in imperial units. We have taken care of the individual particles. Then we'll look at the mass center. Okay, it is also moving, right? This O is also moving at 4 feet per second given by the question. So we will calculate the kinetic energy that created by this moving mass center. Or we can just think of it's another moving particle here, the O. Here, when we are calculating the mass needs to be contain not only the cart itself, you also need to include the mass of the 4 balls, the 4 smaller particles, because they are part of the entire system, right? Because we need the mass center. The mass center's mass is given by the entire mass of the system, which is the cart itself plus the 4 balls right here. Or you can think of they are inside the system boundary we draw at the beginning. So we have the mass calculated as the mass of the cart plus the 4 balls. Okay, the cart mass in slug and the 4 balls in slug times 4. Finally, the total kinetic energy can be calculated by adding up the mass center kinetic energy, 11.2, we just calculated here, and the individual balls kinetic energy, all summed together, 26.8. So the total is 38 feet pound, the total kinetic energy for this system. Okay, for those examples, if you really want to comprehend it, you probably need to watch it over a couple times. The last example I have is a very classic one. Right? After reading this question, you should realize this is a very common question you would see in almost any book that talk about energy, right? Any physics book or mechanics book. So conventionally, or say most of the time, the roller coaster would be treated as a particle. That is, we're assuming that this is simplified to having a dot that moves along the track, okay? Instead of a set of carts, there are dots moving from top to bottom. Then, according to the energy conservation theory, we have mgh plus 1/2 mv1 square equals to 0 plus 1/2 mv2 square. If you set your datum right here at the bottom, then we can get the velocity right here is 74 kilometers per hour. Okay, this is what we would do traditionally when we're treating this roller coaster as a particle. However, when you do not want to treat the roller coaster as a particle, or you cannot treat it as a simplified particle, you need to really consider where the mass center is, because that is where everything relates to. Here I have provided you with the location of the mass center right here, which is slightly under the curve, right? And 17.26 meters above the datum. Therefore, based on this, the height difference of this roller coaster truly experienced from top to bottom is only 17.26 meters instead of the whole 18 meters as we used here in this case. So this would change your answer of velocity 2 to 72.7 kilometers per hour. Right? Well, you can see there are some difference, but not much. If I run this up, this will be 73. So this will be 73 versus 74. So this is really serving as a reminder to you that a lot of things we do in this course and in probably many other courses you're going to take in the future, when we are simplifying a scenario, there will be some differences between the simplified version versus the reality. Sometimes the difference is large, sometimes it's small, depending on what we are dealing with. Okay, so these are the 3 examples of chapter 4. I'm not requiring you to explicitly solve any questions in chapter 4, but you need to start to think about or remind yourself from time to time when you are treating a moving object as a particle, how is it going to make a difference when you are not treating it as a particle versus you can treating it as a particle. Okay. In later chapters, we will revisit this concept a few times as needed. We'll have some examples, but I will give you plenty of reminders and plenty of reviews when we do. This is it. Thank you for watching. I'll see you next time.